Buenos
Muy
días
bien.
a todos los que se nos van a unir.
Buenos días.
Rápidamente voy a cambiar a hablar en inglés para que Michael pueda unirse, por supuesto, a la conversación, pero solamente quería saludarlos a todos y a todas las que se unen esta mañana. Creo que estamos muy puntuales, lo cual me alegra mucho, y vamos a partir en un segundo. Solamente voy a dejar de... Bueno, voy a mantener esa presentación ahí. Bueno, en primer lugar, como les decía, esta charla va a ser en inglés y justamente en honor a nuestro invitado voy a hacer el cambio a ese idioma. So welcome to the seminar cycle entitled Economic Evaluation of the Mega Drought, the international experience organized by the Vice Rector Office for Research and Development of the University of Chile and the Center for Climate and Resilience Research. As you may know, this cycle consists of 3 presentations. We already have one. In fact, I have the one that we already, let me go to this presentation. We already have the one by Josué Medellín Azuara almost 1 month ago. And now we have the very exciting possibility to hear from Dr. Michael Hahnemann. I will make a presentation of him just in a few minutes. So again, thank you to all of you for joining us and participating in this seminar. For those who participate or miss the seminar in April, we have this recorded, and Josué was kind enough to allow us to share this video. So we will share by the chat in this occasion what is the place where you can get the video from Josué. So before I go to introduce to Michael, let me give you some background, very basic background of the mega drought in central Chile. This idea came to our mind a few years ago, I will say around 2015, when we have a drought that's at this moment has extended for almost 4 or 5 years. And we found that this was pretty extraordinary because we are used to have droughts of 1 or 2 years, very intense drought, but having a 4 or 5 year drought was already something extraordinary. So we start working on this issue with colleagues both in the Center for Climate and Resilience Research and outside the center. And we even create something that we called a report to the nation called the mega drought from 2010 to 2015, a lesson to the future. Well, and since then, the drought has continued, and we have seen so many impact of the drought, both of course on water resources, but also on vegetation, on the amount of forest fires, the amount of water that has to be distributed by truck, etc. So we are ending almost a decade in which we have had all the years has been consistently before the average and well below the average. So now it's even more pressing to understand not only the causes, but also the consequences, and in particular, the social and economical consequences of this drought. We read in the news and in different publications that there is obviously effects in the economic activities, but in some sense, we have to get together and produce something systematic on this evaluation of the mega drought, the impact in the social and economical activities of Chile. And this is not only important because of this event, but when we look ahead, and the same happened a little bit in California, and the same happened in Australia and South Africa, the future, unfortunately, the future looks dry. So our idea is that we have to learn from this experience, from this mega drought, because even though I believe that the future is not yet here, the future will be like this, okay? So we rather understand what works and what doesn't work and try to project ahead of these changes. So again, just correcting a previous slide, as I said before, the mega drought has extended. Even today, we are kind of in a dry situation, beginning the 12th year of this drought. And again, we said that we get some lesson from the future, but I think that this work is not complete, and we have to continue advancing in this arena. So this is just a very brief introduction of this. So as I said, today we have the honor of presenting to Dr. Michael Hahnemann, who will give us the presentation entitled Economic Consequences of Drought, another view. So we are very excited about this, as Guillermo said before, looking forward to this presentation. Some of you know Michael, but for those who don't know him that well, Dr. Michael Hyman is Professor of Economics with the W.P. Carey School of Business and the Wrigley Chair in the School of Sustainability at the Arizona State University. He's also the director of the Center of Environmental Economics and Sustainability Policy at the ASU. Prior to the ASU, he was the Chancellor Professor and Professor of Environmental and Resource Economics in the Department of Agricultural and Resources Economics at the University of California, Berkeley, where he served from 1968 to 2011. Now he's Emeritus Professor there. We take the opportunity to thanks again to Michael for participating in this forum. We remind attendees that we will get some questions from you through the Zoom using the chat facility. So send us this question, and Guillermo, Felipe, and myself, we will try to organize this discussion after Michael talk. So once again, I want to say thanks to Michael, and now I will stop sharing my presentation. And Michael, please go ahead. You can share your screen and put your video on. Thank you so much.
So it's a great personal pleasure to be with you. And it's a pleasure to be with Felipe, who was a wonderful student and a wonderful economist to collaborate with at Berkeley, and to be with Guillermo, whose work I've long followed and admired. Another student, Sebastian Vicuña, I was on his dissertation, and it was a very impressive piece of work. Let me share my screen. Okay, let me go to the beginning and let me do this. So just a little bit of context and biography. I came to Berkeley actually in the fall of 1976, and that was a severe drought. And at the time, I was happy, maybe the only person in Northern California happy, because I thought California was supposed to have sunshine all year, which is true in Los Angeles, but not in San Francisco. I grew up in Manchester, which is a very wet and miserable part of England, where it rains. And so it somehow was natural to become interested in the economics of water. I started reading about California. I created a course. Creating a course is the best way to learn a subject, because you have to know the material at least 5 minutes before the lecture. Through an engineering colleague who was a social friend, I was asked to serve as the economic staff for the California Water Rights Agency. It didn't have any economists. That's why they asked me. And I did that while being a professor, and that lasted until I worked without pay. I was fired because I was considered too biased against Southern California by one of the commission members, but I've continued to work on California water. In 2003, I was asked to create a climate change center at Berkeley, which focused on economics and policy. There was a parallel center at Scripps, and your next speaker will be from Scripps. The person I worked with at Scripps was Dan Kayan, and we had a wonderful partnership. I moved to Berkeley 10 years ago. I kept working on California. I was working mainly from 2003 until 2014 on the economics of climate change. But then California had a severe drought in recognition in January 2014. And I put aside my climate work, which looked at risk and some topics that I'll mention. And I went back to water rights and water marketing. And that's what I worked on mainly. in recent years and look forward to collaborations with you. I have a Chilean student at ASU, and there'll be a conference soon in Chile on that topic. But so we had a drought. Essentially, 4 weeks ago, we were worried. And in the last 4 weeks, we have a state of emergency in most of California. So the background, the context is we had a major drought 2012 through 2015. January 2014 was when everybody panicked. And that's when I switched from climate change to water rights. Most of 2016 was normal, 2017 was wet, 2018 was normal, and it got dry. The last 2 years were the second driest pair of years in the record, which goes back to 1896. This winter, going into the third year, was very dry. California has a climate, a Mediterranean climate, I think like Chile. Almost all the rain, 95% of the rain occurs between October and March, and occasionally early April. 75% of the water use is April through September. Also, 2/3 of the water of the precipitation is north of Sacramento. Two-thirds of the water use is south of Sacramento. So we have the perfect mismatch. The snow in the mountains represents 1/3 of our storage. The rest is man-made storage. Last month, and the rainy season normally ends the end of March. The end of March has ended, April has ended. We have an inch or two, in the farm, an inch maybe or less of rain from April through September. This equals the amount of snow in the snowpack, the amount of water equals the record, which since 1896, which was set in 2015. So we are heading into, this would be the third severe year of a drought. And who knows what will happen next winter. So I mentioned that I moved to Arizona State. I'm speaking to you from Berkeley. It's cold, but sunny. I like to say that I moved to Arizona to diversify my water supply, because Southern California gets water from the Colorado River, but not Northern California. But of course, Arizona gets water. So I have a home in Arizona, I have a home here. If there's water shortage here, I can go back to Arizona. So that's my own personal adaptation. I want to talk mainly from the perspective of California, because that's what I've studied almost all of my career. And I want to talk about this primarily as an economist, and I'm going to emphasize the issue of studying the economic demand for water. So first, let me emphasize, I work a lot on non-market valuation. So I'm very interested in the impact on consumer well-being from water shortage. And I work on the valuation of nature. And so I'm very concerned and interested in valuing the effects on ecosystems and vegetation and so on. This is a beautiful house. We built it 23 years ago. We bought the land 25 years ago. 6 months after we bought the land, there was the worst wildfire in California's history in 1991. In the last 4 years, we've had 2 or 3 even more severe wildfires. So everything, 3,000 houses around me, everything around me burnt. This was a bare lot, so there was nothing to burn, but everything 3 houses escaped the fire out of over 3,000 in this area. So I'm saying this because I'm very aware of the diversity of impacts of drought. But I want to focus on how economists think about drought and how they measure the market losses of drought. So, and I want to talk about 2 things. The main thing I'm going to talk about is I don't think we model the demand for water correctly. And therefore, we don't model the loss of profit if there's a water shortage. That's an issue for drought, but it's also an issue for normal circumstances without drought. It's an issue for the analysis of water marketing in general. And that's a subject I won't address in my comments, but will come up in another conference in July. The other thing I want to say, and I'll emphasize, is, and this is a separate talk also, California invented the water rights that you find in the Western United States. Because it was the first mover, California has been the most incompetent in administering water rights. And our dysfunctional water rights are a major impediment to adapting to climate change. I'll answer questions, but I want to focus on the economic modeling. And so I want to argue we go wrong in 2 ways. If you're thinking of a short-run drought, a lack of water in 1 year or 2 years or something, we actually overstate the losses. We understate the flexibility of use. On the other hand, I think we understate the losses from a prolonged drought. And let me say right away, we tend to model things looking at 1 year in isolation. Now, there are models which take a 35-year horizon, but they fundamentally treat 35 years as 35 replications of 1 year. And so we're used to, and we understate the flexibility in a 1 year time frame, but we overstate the accumulation of problems in a prolonged time frame. And there have been prolonged droughts. A 100-year drought, according to the tree ring evidence in the Middle Ages, and nothing very long since white people have occupied California, non-natives. So the key problem is the exaggerated role of optimization in economics. Whenever I say this, my good friends Tony Fisher and Carey Smith have heart attacks, or at least become faint. But I apologize if I upset anybody. Optimization, it's important to know, comes in 2 ways. One is economists measure a production function in some manner and then optimize the water use. But the other approach is they get empirical data and they fit a statistical relationship. That, so far, that's fine. The problem is they interpret the statistical relationship as representing the first order conditions, the solution to a fine-grained optimization. And that's the bit that's not true. The statistical relationship may be valid, but you can't make inferences based on assuming it's an optimization. So I came to Berkeley in 1976. Dick Howard joined the faculty at Davis. He did an optimization model for his thesis. He's retired recently from a very distinguished career. We have differed this whole time, 36 years now, about the merits of optimization. And as I say here, California is a stress test for optimization. So most states in the Midwest grow 5 or 6 major crops. California grows at least 85 major crops. And trying to fit a model which explains why there is some acreage for each of 85 crops is a Herculean task, and it's actually an impossible task. And so the models can't do that, except by artificially constraining the analysis to grow these crops. But then it's the constraints that are driving the analysis. Most of the time, the models are static and deterministic. So much of the hydrology in the US consists of using historical records. So right now we have 86 or something like that years of records, but that doesn't catch uncertainty. You know what will happen in May 10 years from now because the historical record tells you what happened in May 10 years from, this year in the cycle. The analysis, so two things kill you in modeling or make it difficult. One is the time dimension. You can do this on an annual basis. Most of the California models run on a monthly basis, but decisions are not made in the same way on a monthly basis. You decide in the spring what to plant, and then you have some decisions while it's growing, but you don't in August say, I'm going to install drip irrigation. I haven't used it since March, but this month, there's a lot of constraints. Fixed inputs in general, a model as though they're all rented on an annual or monthly cost. So if you want more of a fixed input this month, you can get it. So these are all not realistic. The other thing, in addition to temporal dimension, is the spatial dimension. So this is the yellow is the Central Valley of California. That's 6 million acres. I apologize, I'm going to use Anglo-Saxon units, even though England now uses metric units. But these, 10 is one region, 13 is one. These are big areas with heterogeneous soils, climates, and everything like that. We haven't solved the problem of modeling water and economy, those interactions, in a manner that deals with the spatial and temporal scale. And let me say, I see this as a computing problem. Because you need to move from one scale to another scale in the modeling. You can't just set up one model and run it because you can't handle the dimensionality on the water side, which maybe needs to be weekly or bi-weekly and the spatial scale. So next point. I've been seeing data, I've been doing this since the 1980s. And whenever I have seen microdata, say on agricultural or urban water use, or manufacturing water use, you see farmers who appear to be in the same location with the same soil, growing the same crops, even using the same irrigation technology, using very different amounts of water. I mean, it's the same thing if you surveyed students at the university, 100 students, and asked them how long they brush their teeth or how long they take a shower, you will get a distribution. That's the thing. And so this is from a dissertation done in 1990 by Lloyd Dixon. He interviewed about 45 farmers in Kern County, which is the major farming area in the southern part of the San Joaquin Valley. They're growing, and so he has the crops and he has the irrigation technology. So if you take cotton with flood irrigation, which was common then, less common now, the ET was 3.2. Some farmers applied 2.7, some applied 4.1. You have almost 100% range. Oh, I'm sorry, 3.2 is what the programming models assumed. That was the sort of correct amount of water. And similarly with the other number. So, for example, the difference between sprinkler and flood irrigation, sprinkler is more efficient, was less important than the variation between the least efficient sprinkler and the most efficient sprinkler, or whatever. So very quickly, something is going on. Well, you could think of this in terms of frontiers. And economists have fit cost functions for urban water use as frontiers. We haven't, as far as I know, fit demand functions, where the frontier would be the best practice. but what you observe is deviations beyond it. Those are statistical models which should be estimated. Let me skip this. Let me tell you about Broadview. So I actually got to know this in 1986, okay? This was a small district. The soil was high in selenium. They over-irrigated. They generated a huge amount of tailwater, which was highly contaminated with selenium. It drained into a bird sanctuary. The bird sanctuary was causing deformed birds. The birds on the flyway laid their eggs there, and the birds grew up with horrible deformities. I was doing the analysis for the state water agency, and the original idea was treating the water, but instead we decided they should just use pricing to get them to stop over-irrigating. These were, but separately, the district came up with the same idea. So this, I had thought of it, the district did it separately. They went to a rate scale like this. This is what they paid before, but if you use, so they wanted a 10% reduction in average use. And then if you wanted to use more than that, you could, but you paid whatever, there was this big increase in the price. So you could use more water, but you pay through the nose to do it. So the scheme is implemented between 1990 and 91. So there are about 20 fields. Okay, and this shows the distribution of water use for the 5 years before the change. And you see a wide spread, almost 100%, that the highest use is almost twice the lowest use. This vertical line is the switch point in the prices that was introduced in 1990. I mean, in 1991. All the use goes away. Almost all the use goes away. Okay, so you get whatever it is, I think overall about a 25% reduction. Was there a loss in profit? Now, at the time, I didn't ask the question and I didn't have access to data to answer it. But in the last 2 or 3 years, I asked this question. We don't ask this question. We have studies saying if you raise the price, demand falls, here's the price elasticity of demand. We don't ask, how's profit affected? We assume profit goes down. So Hendrick and collaborators, this is Kansas, it's over the Ottawa Aquifer, it's severely overdrafted. There are a number of administrative moves to reduce groundwater pumping in western Kansas where this is. This is a particular area where the farmers voluntarily agreed to cut back 25% on their water use. The red is the area that agreed. This is a discontinuity design. The blue areas are farms that didn't agree to do this. That's why the red area has the shape that it has. This was voluntary. They were cutting back by 20%. I'll skip the detail is they cut back 26% in water use. Not because of price, the price wasn't changed, but they recognized the threat of administrative intervention to their water rights, to their ability to pump groundwater. Okay. So the question is, how much profit did they lose? So this was not addressed in the published journal articles, but it was addressed in the cooperative extension report by these authors. And they concluded there was no loss of profit. Costs went down, output didn't go down. Costs went down because they were using less, there was no impact on profit. How is that possible? Well, one issue, and I've only become aware of this in the last 6 months through my own research and through teaching this, and I was going to say, water is a tiny cost of production. I'm going to give you 2 examples. This is Kansas. And the important thing is Variable costs of production are $611 per acre. Fixed costs, basically land and hiring equipment, $287. The total cost of production is just under $900. How much does the water cost out of $900? And you can see, according to this, they make a loss, but so maybe the costs aren't that high. The water cost is $51 out of $900 production cost. So let me tell you, if for some reason you needed to use 50% more water, it would cost you $26. If you're paying $900, the $26 is neither here nor there. Similarly, if you use 50% less water and you could save $26, that's also neither here nor there. Let me show you. So this is something I discovered in the last week. I'm working with a wonderful graduate student, Molly Sears, at Berkeley, and a colleague, Ellen Bruno, a younger colleague on the faculty in my department. We're looking at the Pajaro Valley. It's along the coast. It's near Monterey. It's in Northern California. They have seawater. They use groundwater. That's the only source of water. They have groundwater intrusion. They have their overdrafting, and then makes the seawater intrusion. They set up a management agency in 1984. You see the seawater intruding. The management agency, there's a small town, Watsonville, which is here. It's got a wastewater treatment plant. They treat the wastewater, move it over here, just pump it into the ground to get farmers not to use so much groundwater here. They have to finance this. They are now, so the zone where they deliver water, they only deliver a fraction of the water supply. They charge, so they were charging, $80 before all this began, an acre foot. They're now charging 381 acre foot for the small amount of water they deliver. And in the area they deliver, they're charging 330 acre foot as a pumping tax. That's over and above the cost of pumping. This is astronomically high prices by California standard. I mean, this is at least 50% larger, but more likely 3 times what most farmers in California pay. So how's this happening? And what we found is there's a small price effect, but not a big one. The main effect is salinity and moving to areas with lower salinity. So, that if they're using 3 acre foot an acre, which is probably a bit high, they're spending about $1,100 an acre, which is about 2 or 3 times what other farms. How can they do this? They're growing berries that I knew. Only 2 days ago did I discover how much money they make. Depending upon the type of berries, the gross revenue is between $35,000 and $60,000 an acre. The profit, again, varies, but is maybe $10,000 to $13,000 an acre. If you're making $10,000 an acre and your water cost goes up from $500 to $1,100, what the hell? This is only 2 data points. I mean, that the ones that I want to look at this more. But I think the larger point is that water is a low cost, not just because it's underpriced, but because other things are so expensive, labor, pest management, everything else. And so who bothers choosing the exact optimal amount of water if they are using 3 acre foot an acre? As an economist, we can't assume that's because if they were to use 3.1 acre foot an acre, they would lose money. Or if they were to use 2.9 acre foot an acre, they would make less profit. So they're using 3 because that is the exact optimum. But the whole point is we take the demand functions and invert them as though this was giving us the value of the marginal product, as though they were exactly optimizing. And that's the link that doesn't exist. And so I'm summarizing, I'm not giving, but what we found in California is, yes, there are costs from the drought. but the economic costs were smaller than models predicted. They were small. They were non-market costs, loss of utility, fire, ecosystems, those are big, but the cost to the water users, to agricultural, and I think manufacturing water users, they're not zero, but they're smaller than we model. And I think that's because there's a degree of flexibility or squishiness that farmers can exploit that the models don't capture. Now, on the other hand, what happens when there's a prolonged drought? And the short answer is I have no idea, because we haven't modeled this. Because the way we model it is, we model 4 years by modeling 1 year 4 times over, and nothing changed. Most of the models don't track the depth of groundwater. Most of the models, this is an important point, don't track reservoirs. The water economy models are not measuring how full each individual reservoir is and how much it's being drawn down. So we're ignoring that which is, of course, a key part. So until 2013, 14, 15, California only had 2 years drought. I mean, the official drought period is longer, but the crisis occurred over 2 winters, winter 75, 76, winter 76, 77, and similarly, winter 1989, 90, and 1991, and so on. And I think the way we handled it was gambling that Mother Nature would never give us a 3-year drought. She liked California. She was favorably disposed. And that, Mother Nature let us down in 2013, 14, 15. She broke her promise that we would only have short droughts. The economics of, I'm not thinking about longs. I have no idea how to do it, or at least that's the challenge for us. And so I'm just going to sketch a few ideas and then I'll stop. One is risk aversion. The other is what I call the inverse Le Chatelier principle. So let me start with that. So this is a principle in physics that Samuelson applied, Paul Samuelson, to economics in his famous book in 1944. And it's in economics, it's the idea that the short-run response to a price change, to a price increase, is, what am I saying? Is smaller than in the long run, because you have more policy levers that you can pull in the long run than you have in the short run. But the demand function is more inelastic in the short run than in the long run, but interpreted through the lens of maximization, the economic cost is smaller of a price increase in the long run than the small run, because there's more adaptations you can make. But if you think about water in California, the opposite is true. If you think about water in, Johannesburg, if the reservoir has water in it, a cheap thing to do is to pull a bit more water out of the reservoir. When the reservoir is dry, you can't do that. Maybe you import water, that becomes phenomenally expensive. You get an iceberg or something, which was discussed in California in 1976, towing an iceberg. Similarly, in the short run in California, in most areas, you can pump groundwater. But in the long run, this overdraft is going to destroy the groundwater or make it impossibly expensive. So this is what I call the inverse Le Chatelier principle. It's easier to do in the short run. It's cheaper to do in the short run, but in the long run, it's not sustainable. And there's a quote, Herbert Simons, the chairman of the Council of Economic Advisors, and this was a famous aphorism: if a thing can't go on forever, it will eventually stop, because the people would say it can't go on forever, but then they act as though it could go on at least next year. So risk aversion, some brief remarks. The important thing is what's called downside risk aversion. This is a conceptualization that developed and was applied in the financial literature. And the idea is if you get a windfall gain, that's nice. If you go bankrupt, that's more unpleasant than getting a windfall gain is nice. And so there's an asymmetry in valuing losses and valuing gains. And so the risk aversion is different. If you're a water manager and you have more water than your customers want, you don't get a promotion. There's kind of no particular upside to you. If you have less water than your customers want, that's a big problem for you. And so I think water is all about downside risk. My former student, Mike Kaposky, did a dissertation, and with colleagues at Berkeley, we published an article looking at risk analysis to California's water systems. So here's the diagram. There's a black line, 2 blue lines, and 2 red lines. The black line, which you can't see very well, is these are deliveries to Central Valley agriculture, deliveries of surface water over whatever it was, 80-something years when we did this. So this is just plotting the amount of water delivered. And I mean, it's a finite support because there was a lowest number and a highest number. The blue and red are 2 climate simulations. These were done with the 4th IPCC assessment, not the 5th. But the point, the blue is a low sensitivity model. The red is a medium sensitivity model. And so you need to compare the distributions with the black line. The blue line under the 2 scenarios, one low warm, moderate emissions, the other higher emissions. What's going on, as you'll see in a moment in both cases, is an increase in downside risk. In fact, if you calculate the change in variance, there is virtually no change in variance, but there's a huge change in semi-variance, in the chance of getting short. And we used a programming model of the type I've just criticized, and we calculated profits for farming, using the distribution of 85 years. This is the mean. This is the difference in mean. This is when you add in risk aversion based on downside risk, and the loss is very substantial. What I don't show in this table, if you just did regular risk aversion proportional to the change in variance or standard deviation, there is essentially no loss. This is all driven by downside risk. That's what I want to say. To wrap up, there have been a number of articles. This is from something published last Saturday. Jeffrey Mount wrote a wonderful book on California water. Davis is now retired. And he said, by the time you react to a drought, it's too late to react to a drought. And that's the key. You have to have prepared in advance. It's like firefighting. If the building's already blazing, you're not going to rescue the building. You may make sure nobody dies, but that's the best outcome. So this is all about insurance. And insurance is all about risk aversion. Because if you're risk neutral, you don't buy insurance. And I would say it's about downside risk aversion, which magnifies things. So it's about insurance. And the other thing is, it's about making changes to water rights and water institutions that are, in California's case, 107 years overdue. And that's because California reformed its water rights in 1914, 6.5 years ago. And they made decisions to avoid changes that water users opposed and to avoid doing things that other states subsequently had done. And the result, and this is a separate talk, is California has, I think, the most dysfunctional system of water rights. And if not just water rights, we don't have good records on water diversion. In fact, we're working on a project now, how the Water Rights Agency could assemble better records. And we interviewed the staff, and they said it'll take 10 years. So that was 2 months ago. Unfortunately, Mother Nature should have waited 10 years before giving us the present drought. So just to wrap up, the large issue, and this is a challenge for a lot of economics, particularly water, is short-run choices are different. Short-run decisions are not the same as long-run decisions. But for the most part, we don't really model those differently. We model everything as though it's a current decision. And we need to think hard about how to model those things. And let me just end up, it's relevant to drought. And the last word about water marketing. You know, and that's a separate project with Jorge Messias and hopefully collaboration with Guillermo and others. Water marketing serves two functions. One is short-run flexibility. It's a dry year, I'm a water user. I could do with 10% more water to finish off my crop. Or conversely, I have a bit more water than I really need this year, so I could sell some. Flexibility has a real economic benefit for the supplier and the user. The other thing is long-run reallocation. Long-run reallocation because of population, agriculture used to use 85% of the water in California, 50 years from now, it's not going to, and then climate change. The surface water is going to, most of the economic models of water marketing claim to be measuring long-run flexibility. What they are actually simulating is short-run flexibility. Most of the water market transactions in California, like 85%, are short run, not long run. And so there are two questions with water marketing. How can we model the distinction between long run reallocation and short run flexibility? And will water marketing give us the long run reallocations that we need? Those are questions, like everything else I've done, for the future. So let me stop the sharing my screen unless there's some specific questions and take
Sure. Thank you so much, Michael. You know, I am a climatologist, but today I became a little bit of an economist. This was a great talk. In 40 minutes, you give a really nice overview of what we know and what we don't know. And I am particularly interested in this idea of this separation between, as you said, this short drought. We are used to this, even though we not always react in the right way. But anyway, this was our previous enemy. But now, when you said the long run, remember that we have had here in central Chile a 10-year long drought. So the issue cannot be more relevant for us, this distinction between the short run and the long run. So this is very nice. So we have roughly 10 or 15 minutes maximum. And I will see if there is question with Felipe from the public. But we asked Guillermo, my colleague Guillermo Donoso, to formulate perhaps some reflection or some question to Michael. So Guillermo, please go ahead. And in the meantime, if somebody has a question, please let us know by chat.
Thank you, Rene. Thank you, Michael, for that excellent thought-provoking presentation. It becomes clear where the research priorities are and what we should focus on. Just a few comments before a couple of questions. I totally agree with optimization is a misrepresentation of farmers' decisions for the reasons you mentioned, and the need to fit demand functions. Now, the first question when we look at demand functions, how do you deal with let me put it this way. It's easier in annual crops But a demand function, when your decision is long-term, like perennial, then I'm not clear how you can model it correctly. Once you have lock-in, the demand function would tend to be very inelastic. So we would have to adjust, and I'm not sure how. I don't know if you thought about that. With respect to the Le Chatelier principle, totally agree, but once again, once you've taken the decision of investment in fruit production, perennial, you have lock-in, and therefore, I'm not sure if the principle will apply correctly there. Thank you for the presentation on downside risk. That is critical. There is evidence, and here's the next question or reflection. Water as an input is a downside risk reducing input because it shifts mass from a high risk to a lower risk. And therefore, for example, if you have large infrastructure, you tend to reduce the resiliency to drought. So that is essential. And how to model that in these large impact models, I'm not sure how to incorporate it. It is fairly well dealt with in annual decisions, but in the long term, I haven't seen good modeling. I don't know if you can help us there. And two final comments. In the overestimation of costs due to droughts, I agree. Water use efficiency, the estimates of Frontier with the development analysis, shows that even very high efficient farmers, drip irrigation, have low water use efficiency. They're about 40% off from that Frontier, which gives them a space to improve their productivity when they're really tight. And that's another issue to consider. And water marketing, just one last thought, if you can reflect. A long-run reallocation in itself is an insurance. I'm willing to buy more water rights than what I need today, as is the insurance for water allocation in drought periods. And therefore, what we would consider non-use today is a premium I'm paying for long run. So that was a general comments with questions in between.
First, I agree with your observations. And the other thing I should say is, I'm asking the questions, not answering them. But what I really, no, but I would like to, I see this as a research agenda,
yes,
you know, for me and for other economists. And I'd love it if we could collaborate in pursuing some aspects of that agenda. But let me take more questions, and then why don't you give me a group of questions, and then I can answer them closer to the end, just to hear more from people.
I'm processing and trying to put some together, Michael. So if you want, go ahead with these reactions to Guillermo's comments.
One point I should, I'll make one point which I should have mentioned and didn't. So yes, they have slack, and so they can use less water. The question, though, is at some point, you know, if you have a 10-year drought, maybe they run out of slack, and then it's a big time. So slack, so I wanted to emphasize, I'm aware of this two-edged sword. You know, on the one hand, the slack, and so for the short term, we overstate things. But on the other hand, when, you know, it's called in California, demand hardening. And the question is whether conservation is a renewable fruit. So it keeps growing back, so they're low-hanging fruit, or whether at some point it stops being renewable. And it's also, of course, a function of time. If more time elapses, you can discover, you know, better ways of doing things. And so California is stuck because we had only 3 years. And we face it again, but if you have 10 years in a row, But I wanted to emphasize there is slack, but it's not an infinite supply, and that we need to figure out how to model this in a reasonable way.
Yeah.
I see one question. California, 4 years ago, declared a human right to water. It's the only state which has it. However, California doesn't really, having declared it, it's very difficult to do something about it. So this is an issue, on the drinking water and water supply in urban and poor areas. Urban water supply, that's another topic I work on. It's immensely expensive. And so one solution is people should move to live in an area where there's a connected pipe water supply. I know that's difficult, but producing water to satisfy a human right to water is tremendously expensive. It's much cheaper to give everybody a cell phone than to give everybody good access to drinking water. And so California has set this goal 5 years ago, and it's working sincerely, but there's no solution in sight, partly because you have small, inefficient, scattered systems, partly because you have poor people, particularly in farming areas with no connected water supply system. The solution is subsidies. Some people have to pay money to subsidize other people's drinking water. And, the United States in general, isn't good on altruism and government investment. So, but do you have other questions?
That's a big question, and I think that's connect with one of the last questions that I have from Camila, precisely Bottinger. Thank you for the presentation. Camila, I don't know if you want to read your question or
I
go
think
ahead.
I answered it. I saw it in the chat. So I answered it.
Sort of answered. My question was if this is a legal. I'm a lawyer. I'm not an economist.
Yes.
That's a legal, it's a variable that can influence the risk, because if you're second in line to get the water, but the sanitaries or the utilities have the first use, it changes.
No, I agree. So in some sense, so I'm not a lawyer. I want to be a lawyer when I grow up. I still do, but, and I have been involved in litigation, but I think that's not going to have legal force because it requires money and there's no money.
The thing is, in Chile, we're having that problem now.
Yes.
The jurisprudence is giving the right to 100 liters per day, despite the cost. So it changes the scenery for us.
Interesting, yes.
If you need a lawyer, just call me.
There is another question, Michael, maybe you could address that. I think it's quite interesting. I know that you can talk for hours about this issue. The question is from Laura Mesa, is about the non-economic impacts of drought and its valuation. So,
well, valuing the impact on ecosystems and what people would be willing to pay to protect an ecosystem, we can do that. We, in the sense of you, Felipe, and I, we know how to do that with stated preference. And then there's the loss of utility to households if they are forced to conserve. And on the one hand, there's a willingness to do your part, but maybe after 5 years, the willingness goes away. We haven't experienced it in California. But those are things that can and should be measured. And there's also, as you know, a literature measuring the willingness to pay for insurance in the sense of investing in infrastructure that would make a more reliable water supply. Let me mention one thing. I've been involved, as I say, as the economic staff of the California Water Rights Agency. Big fight, 33 years ago between water users in cities and farms and environmental groups. What I observed was agreement, consensus on one thing. Nobody wanted non-market valuation to be performed. The water users, because they were frightened the values would come too high, and the environmental groups, they were frightened that the values would come too low. And the result was a sort of tacit agreement not to value these things. I, as staff, was not supposed to do independent research. We had hearings, there was a legal process, we could only use information, and lawyers cross-examine witnesses, so we could only use the information in the records. So I knew how to do the valuation, but as the staff, I couldn't do it. And there is this element of fear and loathing of economics because it may produce an answer that you hate. That's...
Thank you. Sorry about that. There is several questions that we have addressed partially, at least. Here there is one from Francisco Fernandez. It's slightly more technical. I will read for you. The question is, when microdata is not available or aims to assess the economic impact at an aggregated level, do you think that maybe optimization could be acceptable? If it is acceptable, what point must be addressed with more precaution? He's a little bit concerned about using these optimization models, I guess.
Yeah, no, I understand. Well, so what needs to be done? I had a long-standing dispute. First of all, I would run an optimization model with constraints that are realistic. For example, after March, you apply the same amount of water, and you don't make a separate decision after April. You don't make separate decisions in May, June, July. And if you purchase water for water marketing, it's not month by month. It's 3 months or 6 months. In other words, to make the decision making a bit more rigid would reflect some of the reality just through constraints. The other thing is, and I'm interested in look, I'd like to analyze microdata and then compare the results if I did an aggregate analysis, but see if I can develop a statistical correction factor to apply to the aggregate that gives me what I find in the micro. It would be an assumption that the statistical, correction applies. But that's an area I would like. I'm actually trying to do this with colleagues at Riverside on urban water demand, where you only have data on the rate structure and the average per capita use. But you actually have a whole distribution of water use and distribution of income. And so you sort of want to know how rate structure harms low-income people, but you only know the average water use. For some places, and for other places, you have all the data.
Great. Guillermo, I don't know if you want to make a final comment or remarks, and after this, we will start to finish. I just will give a few announcements, but Guillermo, please go ahead if you have something else.
Thanks, Michael, for addressing all of these questions. I do take home a question that is for my reflection, and I'll leave it for others. How much responsibility is the lack of good economic valuation of the cost of droughts on the fact that policymakers tend to use disaster management and not risk management?
Yes.
Yeah, that's encapsulate many of the things that we have discussed. When we proposed this series of seminars, and we are in the second of 3, we precisely said we want to share experience and learn what people are doing. And I think that's we are doing exactly this, what we promised. And we thank so much Michael for all, not only his knowledge, but his insight on this issue. It has been very opening for me and for many others, I'm sure. So once again, Michael, thank you so much. There was a few questions that I write here, and I may send you later today.
Yeah, no, by all means. So my email, so just people should free to email me with comments or questions. I have an ASU email and I have a Berkeley email, and the Berkeley one is shorter and they all come to the same place. Excellent, so Hanneman at Berkeley or michael.hanneman@asu.edu, they all wind up. So by all means, send me comments.
This is very generous. This is very generous from you, Michael. We appreciate this so much. And again, thank you to all the audience. We limit this to 1 hour and a few more minutes to don't extend too much. As Felipe said, we could talk for hours, and I hope that we will talk for hours later. But time is finishing, so we will start to finish this presentation. And I want to invite you to the next seminar that will be roughly in 1 month from now. I don't remember exactly, but it's the last Tuesday of June in this case. And we will continue talking with colleagues from California. And even though we have emphasized the drought, and again, we have this very long lasting drought, we always have to keep an eye on extreme events in the other side, right? From time to time, we have this flooding. We have one big one even in January, and who knows what can happen this year. So in the last talk of these seminars, we will have Tom Corrigan from University of California, San Diego, and the Scripps Institution of Oceanography, precisely talking about the economic valuation of atmospheric rivers. This is a new name that we meteorologists create for this big storm. So it's something that's very relevant also for the Chilean climate. So again, I want to thank Michael. I want to thank Guillermo Donoso, and Felipe, Susana, and all the other colleagues that have helped us with these seminars. And have a great day, Michael, and have everybody here a good afternoon. So thank you so much.
Bye-bye.
And
thank you.
We'll be in touch. Thank you to all of you.
Bye-bye.
Bye-bye. Nos vemos.
Muchas gracias, gusto verlos. Hasta pronto.
Muchas gracias a toda la audiencia.
También, cuídense.
Vamos a compartir después el video y la presentación de Michael en nuestra página web.
Chao, Felipe.
Chao.
Bien.